The curved one's really nice because any light that passes through the curved side, it's going to be going in at exactly along the normal line. And so we can use a curved prism, curved one side, flat the other, to really investigate in more detail what happens. And so if we shine the light straight in, it goes straight out. As we increase the angle of incidence, look how as my angle of incidence kind of maxes out, the refracted light, it's not maxing out at all. It can still go like, it's still refracting. Do you see how we're not maxing out this angle of refraction here? So the thing I want us to think about then is, what about if we do it the other way? What about, we're still thinking about the light bending at this flat bit, but what about if now we're thinking about the light going from the perspex back out into the air? When that light's going in straight along the normal line, it still goes straight out, but as we increase our angle of incidence, you see that the angle of refraction's greater than the angle of incidence. So what's going to happen? Eventually, as we get up to that maximum possible angle, how much light is being refracted through here? None. And so when we're going from a more dense to a less dense medium, we eventually get to some point at which the light no longer passes through. It no longer is able to refract, and all of the light is reflected back into the same medium. This is the trick that fibre optic cables use to transmit light down, like signals at the speed of light. They have a really high optical density core and a really low optical density sheath around it, and so the light is trapped inside the fibre optic cable and travels down it. It can't escape. It's very low losses. And so the angle where we lose that refraction, something like about there, do you see there's just a tiny little bit of light still being refracted? That last angle where the light's going in and then it's refracting at 90 degrees to the normal, that's the critical angle, we call it. The angle that the light goes in at, we call it the critical angle, because that's the angle that we swap over from refraction into reflection. So if we make the angle a little bit smaller, look, we're getting heaps of refraction. If we make the angle a little bit bigger, we're getting no refraction at all. And so that angle, that special angle where things swap over and we just start getting a little bit right there, is the critical angle. That's the angle of incidence that causes an angle of refraction of 90 degrees. Okay, so there's three different phenomena. There's what happens when the angle of incidence is quite small. So I'm going to do three different phenomena, three different colours. Hold on to your seats. That's theta I is small, and as it goes from a more dense to a less dense medium, that light is going to get refracted away from the normal. So that's refraction. Going from more dense to less dense, small angle of incidence, the light is refracted away from the normal. The second thing we're interested in is the critical angle. And so the blue one, that's our angle of incidence, is critical angle. The critical angle is the angle of incidence that causes refraction that goes along the boundary like that. The angle of refraction is 90 degrees. We're going to come back to that in a moment and calculate up how much is that critical angle. But first of all, as soon as that angle of incidence gets greater than the critical angle, we move over into the territory of total internal reflection. And that means that none of the incident light is refracted into the second medium. All of it is reflected back into the first medium, and the angle of reflection is equal to the angle of incidence. We just go back to that classic rule of reflection, that in angle is the same as out angle. Of course, this reflection thing, like we saw, it does happen at the other angles. Like, even for the normal refraction, there is a little bit of that light, that green light, is reflected back, but we don't normally talk about that. We normally exclude that from our diagrams. And the same with the blue one. There's going to be some light that's reflected off. What we're interested in is when all of the light is reflected, none of it is refracted. So what we're going to do is have a go at calculating critical angle for light going from glass to air. And so what we're going to do is we're going to use Snell's law, but we're going to substitute into Snell's law. Instead of theta I, we want to know the critical angle, and we know that the critical angle occurs when theta R is 90 degrees. Excellent. Who knows sine of 90 off by heart?
Is it 1?
That's 1. N2 times 1 is just N2. So we can rewrite that equation much more simply. Look, N1 sine theta C is N2. That's not on your formula sheet. You have to be able to go from Snell's law to finding the critical angle. And the things you need to know to do that are that theta R is 90 and that theta C, the critical angle, is the angle of incidence that causes refraction at 90 degrees. You don't have to remember that sine of 90 is 1. You could work it through with sine of 90 in there and you're still going to get the right answer. But it's more elegant if you know that sine of 90 is 1. And so we have to rearrange this to make it equal to theta C. What am I going to do first?
Divide by N1.
Good. Divide N1. We do the same on both sides of the equation. And so we end up with sine theta C is N2 over N1. What now?
Sine -1.
Yeah, we're going to inverse sine it. So theta C is the anti-sine of 1 over 1.5. Notice that the value of that fraction, 1 over 1.5, is less than 1. Sine, you can only inverse sine something which is less than 1, between 0 and 1, right? If you try to inverse sine something that's greater than 1, you're going to get what Luca got. You're going to get math error, syntax error, something like that.
Math error.
And that's because if we think about what a sine graph looks like, it wiggles up and down, above and below the x-axis, and the maximum value that that sine graph ever gets to is 1. And the minimum value it ever gets to
-1.
is -1.
Yeah.
So normally with triangles, we're never expecting to have an angle of greater than 90. We're working at this region of the graph here. So what you're asking your calculator is, I got sine of this, how much is the angle? If you say to your calculator, I got sine of this, how much is the angle? Your calculator's like, but there's no line there. You're wrong. There's a mistake. That's why you get math error. It's not possible to find a value for sine greater than 1. And so, the thing that happens to people when they're doing this calculation is they'll often get that fraction the wrong way up, and you'll get math error. Probably the thing you need to do to fix it is flip your fraction, and it will work.
What if it doesn't, so?
Just go back and start again. You made a mistake. Who's got an answer for that?
I got 41.8103.
No, I had that, but I used one maths.
41.8 degrees. Critical angle. Cool. That was easy, wasn't it?